Maybe. We'll just wait a few minutes just to see if we have sound on our post. On the live video? Yes, we do. Okay, I'll just mute myself. All right, hello.
Hi there. So we are together today and we're doing our third podcast.
Vodcast?
Something?
Yeah.
Yeah.
Like a podcasting. Yeah.
And we decided to do it for computing sciences and for the general public as well. And we're having Dani as in the role of the expert today.
Got my title as the expert. We'll see. By the way, and we have Kristina here, who will ask the questions. She is a physicist, and today she got her results from her exams. She's very happy about it. Let's say she's happy about it.
Yeah, I've passed third year.
So
let's move on.
Let's do that.
Thank you.
Today we're in a hotel, and we are slightly blurred, so I'll change the camera to a different one. We don't know why this is happening. It's some kind of auto-tuning of the camera systems. It's some kind of computers. We're not going to talk about this today.
We have the expert here.
We have the expert, but we're not going to talk about cameras today. We have no idea. It's just some stuff happening. So, all right. Anyway, the topic today is going to be something that has been very, very interesting to me in the past few years. This actually came from a question which I got on my interview in 2014 when I was applying to Google, and the question was, it's already public, it's everywhere, so it doesn't matter if I share it. It's what happens when you type www.google.com and you press enter, and it's basically trying to explain everything that is happening on the whole network when you do that. I'll remove my headphone because I hear nothing. So, if anybody wants to complain on the thing that, it doesn't hear anything or something, just give it a shot. Hopefully we have, by the way, the topic today is very ironically the internet. Hopefully we have enough internet in this hotel conference room that we just kind of came into. We are literally on a tennis ping pong table. I just want to show the backstage, right? And yeah, we just set up whatever we have right here, right now, just to make do the podcast. We postponed it, by the way, to Thursday because on Wednesday, usually there is this gathering of our fellow physicists in Sofia, and they usually don't participate in activities which they will be able to watch the podcast, as far as I remember. So that's where we are.
So if you have any other suggestions about a different time or something, please share them in the live chat. I'll take a look at it from time to time. So, Dani,
we'll have this conversation. It's a little bit awkward, but we'll try.
So,
okay.
Dani,
yes.
Because I'm using the internet all the time for my physics research and to pass my courses. So, what happens when you type curiousbun.ch?
We're really new. We don't know our URLs yet, but we'll get there. Okay. So first of all, let's talk about what is curiousbun.ch, right? So this is called a domain name, and it ends in .ch, and before that there is curiousbun. In the example of Google, you have google.com, and then it's in com, and there is Google. But you can also have www.google.com. So these are all different versions of domain names, and they're hierarchical. So what you have is at the end, in our example, we have ch for curiousbun.ch. For Google, we have com, then Google, then www. And the resolution happens from the back towards the front. And there are so many things that are happening when you type this thing into a browser that is just crazy.
And everything happens
usually within a second if you have good internet connection, whatever that means. But it's just crazy amount of stuff that needs to happen on all layers, and that's why I was so fascinated about this question, because you can touch almost all of computer science.
Because it encapsulates everything, like not just the physical thing of pressing the button. So I'm making some electricity flow through some current, and then I have my computer, and then I have some wireless stuff around.
Right. So the first time that I got asked this question, this was at the end of the interview, and I was feeling kind of hyped already, So I started, and I was just starting with a joke, basically, in the jokiest way that you can do it in computer science. So it was basically, yeah. He asked me, what happens when you type this, and I started. Well, first thing that happens is, the enter key makes some kind of a connection, and then some electrons flow through the wires, so that creates some kind of potential difference, and blah blah blah.
And then the guy was like, "Oh my god!"
Yeah, no, he was like, "No, we're just interested in the network stack."
In the easy stuff,
yeah.
Easy.
But how much do you know about these things? Have you prepared? Or?
Wait, I'm asking the questions here.
Like when you press the key, something needs to happen, right? There needs to be some kind of, electricity or like two electrical plates kind of making short, or like it's kind of a switch, right?
I recently read it about smartphones,
Mm-hmm.
like the touch screen.
Mm-hmm.
So you have basically your thumb is closing the not
circuit.
The circuit, yeah,
Mm-hmm.
thanks. It's closing the circuit,
Mm-hmm.
and then you have the voltage in this special place is lower
Mm-hmm.
than the rest, and then you have the transmission of this place, the coordinates of this place go to the software,
Mm-hmm.
and then the software gives the feedback to the screen to show the user that actually he or she pressed the button, and then it's going back.
So once upon a time, it used to be the case that like in old, I don't remember, there were these things called capacitive and resistive displays, but that was like long time ago.
Yeah, you can touch like the old phones. You could touch only one place,
Mm-hmm.
and now you can touch like 3 or 4 different.
By the way, did we find the marker? Because in this room, by the way, we have like whiteboards, but I don't think we have like markers in order to display stuff. Otherwise, I would draw things. Anyway, but basically, what I remember was like you have the display, right? And then on like every edge, or like on certain points around the edge of the display, like if this is your phone, basically here, right? So you would have like points here which would try to triangulate your finger, right? So you would have different resistance through these points, but that used to be the case. Now I don't think that's anymore the case, because this is very, very inaccurate for a few reasons. One, you can't really triangulate this very accurately, and it will be different accuracy closer to the edge and further than the edge, right? Second, you now can do multi-touch, right? You can touch with several fingers on the display, and you can't really do that. However, if you take a really close look at the display, kind of pixels which are within the display itself, which are actually doing this kind of recognition of where your finger is. So they're like a bunch of, like, there is a matrix above the matrix the matrix which you see the display, but there is also this matrix about understanding where your finger is and where all the fingers are. So they're like mini capacitors, imagine it, or mini resistors, I'm not sure, I think it's resistors actually, which are able, or resistor capacitor pairs in some way, which are able to detect that's what I imagine. It's some kind of electronics, I don't know. But they're basically able to recognize on which coordinates of the screen your finger or fingers are. And then they overlay that on the keyboard. So when you turn on the keyboard, you have the keys, obviously. Right? I'm just trying to put on the keyboard just so people can see it. And then you can, like if I tap here, basically it recognizes on which location exactly it was. And then you press the enter, or you press the...
Yeah, and back to the topic, please.
Right.
Right.
But
so
this is still interesting, right? And if you want to get from there, it's still interesting. So you press the enter, right? What happens? Well, first of all, the program needs to recognize where you are, right? It needs to recognize, okay, I'm in the URL bar, so I need to resolve whatever it's there. And as I said, like I have curiousbun.ch or whatever, but Chrome, once upon a time, that was its big thing when it came out. It started recognizing when you type different things on the URL bars, right? You can search directly from the URL bars.
It's guessing that I'm gonna search for curious.
Right. Right. You can instead. So it used to be the case that Firefox had this ability that it had the URL bar where you have to type www.whatever.com, and then you have a separate search field where you can.
You mean that Google in.
Yes.
Okay.
So when Google created Chrome, it called it the Omnibox, And that was, by the way, full disclosure, I work for Google for people who don't know that.
He's not biased at all.
No, but I don't work at Chrome or I work at the cloud, just so it's clear. But basically, it introduced this URL, which used to be the URL bar, but now it created the omnibar. It called it the omnibar, which meant that you can either type the URL address as it is, like with dots and everything, or you can type a search items, as if your URL bar is also the search bar.
And it's redirecting it directly to Google search.
Right. Well, you can change that.
Really?
Yeah. You can go to settings and
but
you can.
Why?
I can't answer this question. You can change it to whatever search engine you want. You can basically you can type the search engine which you like, and then you can substitute caret s caret greater than and then less than s in between, and this will replace whatever search item you have with the search engine that you want.
Wow. Okay. Yeah. I learned.
So you can use Bing or you can use DuckDuckGo or whatever search engine you want, but Google is the best.
Yeah. Okay.
Yeah.
Cool.
So what it does is like one there must be some part of the code somewhere in order to recognize is that a URL or is that a search term. So if it's a URL, it will go through the pipeline where the recognition of the URL and understanding, splitting these dots, which we'll mostly talk about. But just briefly to say, if it is a search item, it will take these search items and then put it in place of this S string and then pass it on to the search engine, which will create its own request, which we'll talk about in a minute. Right? Does that make sense or not?
Yeah, that makes sense. So let's say for the sake of the case that I know exactly the URL and I have typed it properly because I think the other cases.
So let's say curiousbun.ch, right?
Yeah,
which is our website.
So
right.
I know
what happens?
it, and I press enter, and then in few milliseconds I go to a website. What happens in between?
What happens in between?
It's kind of magic.
Yeah, it is. There's a lot of things that happen, and there is a lot of cases in which certain things can happen or they may not happen. Right. So first of all,
what's the first one?
So first of all, right. So assuming you press the enter, right, and then the processor. I know you want to get to the networking part, but there is still so many interesting things happening in between.
Okay.
Right. So
I'm here.
So your processor is actually running a bunch of things at the same time, right? It's not just having the browser. It's having maybe a media player, or it has the operating system stuff that it's running in the background. There's like a power daemon, that controls, what the power levels are, or the microphone, which is now recording, or the camera capturing device, or whatever. There's a bunch of things that are running on the back end.
Okay.
And it needs to, the processor basically switches really quickly in between these things.
It's like a threading.
Yes, so yeah, there's different layers of abstractions. You can have threadings or process, whatever, but basically it's switching between all of these tasks. Right. So one of the tasks is listening to input devices. And the input device can be a keyboard, it can be the touch display, or can be any other input method that you can think of, like mouse click, for example. Instead, like some people just try to type, or they have visual keyboards, whatever. But they have this thing. So the processor is switching on between these tasks, and at a certain point, when the input device creates such a so-called interruption to the processor. So the processor interrupts all the tasks that has been running so far and gathers the interruptions which has been happening from the input devices, but also the output devices like drawing on the screen, etc. But it gets this interrupt and it says, okay, what happened? Well, the enter key was pressed. There was some SIM code which happened.
That's very interesting because it's the same way how our bodies works in a way, because you have the visual stimuli or the sound or something happening in the environment which abruptly stop your brain process. Say you've been dreaming and then you hear a really loud noise and you're like, your brain is kind of, okay, this is much more important.
Yeah, so it gets interrupted, right? It's the same idea.
Same idea, yeah.
It gets interrupted and based on... Yeah. It's a similar idea, yeah. But just with computers it happens digitally and we have analog processors in our brain. I think. Probably.
Another time.
Yes,
Time.
okay.
Okay.
So what happens is the processor says, okay, the enter key was pressed, and then it needs to understand from the operating system in what was the context that this enter key was pressed. Because enter key can depend whether it was on the URL bar, or it was in a text document, or it was somewhere else. Like if you press it on the desktop, nothing happens. But if you press it in a URL bar, then something else needs to happen. So it goes through that pipeline. Now it recognizes that there is an address. Okay. So Chrome now redirects this enter key and it takes it and it says, okay, there was a URL, so we decided, we're not going to talk about, the search item, but we're going to talk about the specific address that was typed. Okay, so Chrome takes curiousbun.ch and it splits it into two tokens. The two tokens are ch and curiousbun.
Okay.
Right. That doesn't necessarily happen on Chrome level though. Right? It can take the whole string that was in the URL and just pass it to lower level libraries. Now, I don't know what the Chrome code does, but we'll just talk it in an abstract terms here.
Okay.
Right? So it may take the whole thing and pass it to lower level libraries code. So it could be the operating system level or some other application layer in order to get that string. But the idea is, eventually, somewhere along the lines, we need to send a DNS request. A DNS is domain name service. So that's a domain name service. It's DNS. So this is the first TLA for today. It's TLA is a 3-letter acronym. Yes,
okay, cool.
That's the first one. There's going to be a bunch, curious bunch. Okay.
I'm still connecting.
Oh, there is a problem with our live stream.
I'm just checking.
I think we have
Do we
it
still
good
have
here.
internet?
Yes, I think I'm good.
Do we still have that's ironic.
Yeah, I think the.
Okay, I don't have internet.
Okay. Well,
Okay.
you can try to reconnect. Just very quickly, just some technical issues, but we're gonna get through them really quickly.
Hopefully.
You can, by the way, the only thing, the only thing that works everywhere on computers is to try to turn it off and on again. And she just tried to turn off the Wi-Fi and turn it on again. So that's what we're doing.
We have 3 people watching.
Hopefully it works.
2 of those are us.
Well, yes. What can you do?
Oh well, it's okay. Oh, we have a question.
Okay.
What happens when I send an email? How email works?
I think this is a topic for absolutely another day.
I'm sorry.
There is, it's a whole bunch, curious bunch of other things that happens there. There are some intersections, like on some layers we can talk about, but it's...
I guess there's a lot more of an encryption.
In emails? I really don't know. I know up to some, like up until some layers which we can talk about, like IP routing, etc.
Yeah, maybe
things
when
happen,
you're
but
explaining the original topic, you can just mention, okay, this works for emails as well, and this is kind of super general, this is more specific.
Yeah, but emails are much more complicated. Like the domain name system, for example, also works for emails, right? Because when you send an email to, let's say, Kristina@gmail.google.com, that's not the real email, but in any way, if you send that email, right, you still have google.com, right, which is still the domain part, which still needs to get into some kind of DNS, like the domain name system recognition.
So,
in order to get it.
DNS.
Right. So DNS, I mean, all of these topics are deep, very deep. Like we can go as deep as we want. Like as I said, like we can go with the keyboard as deep as we want, or we can go with the DNS as deep as we want. But the domain name system works in a hierarchical way. So you take the com part, or the ch part, in our case, and you ask...
Why ch?
Switzerland. Or why Switzerland has ch. It's because it's... That's interesting. It had 4 languages, and in one of these languages, ch is the contraction of how Switzerland is called.
Okay.
Something Helvetica.
Okay.
Because I think in their Romansh language, like they have 4 official languages, right? French, German, Italian, and Romansh. And in Romansh, the name of Switzerland is like something Helvetia or Helvetica.
Okay.
Right.
Okay.
And the C is like kingdom or something.
Okay.
Or canton combination or whatever. But that goes into CH, which is the Switzerland top level domain. By the way, that's another 3-letter acronym, TLD, top level domain. Top level domain. Yes. So the CH, the .com, the .net, the .org, all the country codes, the .bg, .uk, all of these are top level domains. Now there are newer top-level domains, right? There are these .geek and .dev and .info. No, info is old one. But there are all these new kind of cool TODs. Go.
Why UK has have co.uk?
I don't know. That's a trivia question. I have no idea. But yes, indeed, yeah, I don't know.
Okay.
I guess it's a decision by the UK people. UK.
Just
Yeah,
UK
I don't know.
people.
Yeah, because
Sure.
UK has like .co.uk and .gov.uk and whatever. Yeah, I don't know.
Back to the
Back to the
DNS.
topic, yes.
Yeah.
So first of all, there's many levels of cache for this. What do we need to do? I'm almost out. Right, okay. So what needs to happen? So we need to resolve this domain name into a so-called IP address.
Okay.
Okay. So basically, computers don't speak letters; they speak numbers. That's the basic idea. And we need to translate this domain name into some bunch of digits. And the translation process happens with the help of the domain name service. So this is the DNS part that happens. And what I like giving as an example is like you have your own address in Bulgaria or in the UK, you have like your street address and then the town address and then the country address. So imagine your street address, governstreet.glasgow.United Kingdom. Imagine this is the thing that you write in your browser. And the coordinates, like the latitude and the longitude, like 0.
This is the name, the IP address.
This is the IP address in this example. So you can have, resolving the address, which you have like the physical address, which you write a letter to something that the computer would understand, like the latitude and longitude. This is what happens with the DNS. But it's obviously not like this kind of address, it's just a different kind of address, but that's the idea. So if you have something.ch, you would first go and ask the domain authority servers for the .ch. So you would go to the, let's say, in the example of the physical address, you would go to the United Kingdom Central Server, Authority Server, and you ask, where can I find Glasgow? Or in .ch, where can I find curiousbun, right? And then ch will say, here are the authoritative servers for this address. Okay. And you would continue. So for example, in the .co.uk, for example, this is what will happen. You go to UK and you ask, where can I find .co? So you would find the previous prefix of the domain name system. And then you would go and ask the servers for the .co, where can I find the, let's say, government.co.uk. I don't know if it's
okay. So like for the sake of the example, I'm the person going to those places, but here in this example, who is checking the servers?
Right. So Chrome, for example, or Firefox, or whatever browser you're using, contacts these DNS servers. Let's say we're not going to talk about cache for now. Right, so there are well-known root domain name servers which know all about the top-level domains, like the TODs, the .coms, the .uk, the .bgs, .uks, .infos, etc. These are called root name servers, and they are managed by an international, I think it's IANA, the international organization which maintains IANA, IANA. It's just an organization in the world that manages these root servers. So there are many root servers around the world. It's complicated. There are many root servers around the world that you contact for these top-level domains in order to understand who are the authoritative servers for the top-level domains. So you would contact these these
yeah, but it's
root
not
servers.
Me personally. Is it the is it the browser?
Yes.
Is it the okay? So it's the browser.
In some approximations, it's the browser. Yeah, from the top level, it's the browser, but like if you start digging deeper, you're gonna realize, well, the browser actually makes a request to the operating system, which makes a request to your LAN card or whatever internet device. Yes, whatever internet device you have.
Wi-Fi card, one card.
Yeah, let's say
some signal, and we're getting back to physics.
Yes.
Yes. So we have the signal, and it's transferring away from my computer, and then
goes to
we
your
have
local
the-
router,
Yeah.
let's say. The local router connects with your ISP, which is another TLA, which means
Oh yeah, and yeah, the Vodafone or
yeah, or yeah,
something.
MTEL. I don't
Yeah,
know.
okay.
Still
And then they're transferring this signal,
somewhere else.
which is searching for .com.
No, it's contacting the root servers, right? So we're still on the DNS stage. We still haven't made any kind of request. We still have not even like touched anything,
Okay.
right? We're still
So
our
we're
question
just
so
trying
far.
to
Yes.
translate
First,
something.
so let's say there are two big parts of the whole
Okay.
thing. The two big parts are, number one is we want to discover what these words go into what kind of address, like the latitude and longitude, or in internet terms, it's the IP address, Internet Protocol address. So that's the first task. That's the very first thing. Before we even make any kind of requests towards Curious Bunch in order to get the page that we want, yes, we first want to resolve the name. And because this task happens all the time, because we want to resolve, google.com or bing.com or whatever,
Like some standard
any
sites
kind of
that you
website,
visit
yes.
every day.
Because
Facebook.com.
Facebook.com. Anything that you want to resolve, or even on your applications, like on the back end, they do some kind of resolution, right? So when you open your Facebook app, on the back, it's doing actually a request, but you don't see it. There is no URL bar, but it's still doing a request. And these requests still contains two parts. That's the cool thing about the internet. Everything is in the same stack. Even though it's an app, and you think, oh, everything is on my phone. No, it still does requests to the internet, but the URL bar is hidden from you, so you don't see the URL bar. And what is happening?
Which makes sense, because if I don't have internet, well...
You don't see
yeah,
your
my phone
updates,
is-
right?
Yeah.
So it still does requests. It does the requests on the same exact way. And it first needs to resolve the domain name and needs to translate it into 4 digits, 4 numbers. The numbers are from 0 to 255, and there are 4 groups of them. For example, 192.168.0.1. These are 4 numbers. This is a very common internet address. And it will resolve it into something like this. So for example, Curious Bunch, I can check on my computer. Do we want to share the screen and stuff, or do we?
Yeah. I mean,
So
many questions. Oh my god.
do we have more questions?
Yeah.
All right. So I'll just briefly explain. So if you, I'll try to share the screen. Let me just give it a second, because we are really in a completely different environment this time. So it's a little bit more difficult. Just give me a second. I'll share my screen. To screen. Application window. I'll just share my entire screen. I hope everything is okay. Right. So hopefully. If I do, I don't know how much you can see, by the way, from this, because it might be.
Are you sharing the...
Yeah, but the thing is, I think my screen is a little bit too small, so I'll just try to change the font of it. Oh, by the way, I'm not sharing the screen right now. I'm sorry. Yeah, I need to share the screen.
Oh, Inception.
Yes, now it's going to be some Inception happening here. So if I do the terminal here, but I can't, I'm not really sure I can zoom, so I'm just going to try to change the profile and increase the font, because there must be some kind of way to increase. You're seeing literally, oh, there we go, custom font. So I'm going to increase the font so that people on the podcast can see. Let's say 30. Yes, so hopefully this is now seeable.
Seeable.
Lookable, I don't know. And I'm not sure, by the way, people hear still the podcast, by the way. Now, I'll include, yeah, they might not be.
Some feedback. In general, the feedback is that the microphone is a bit...
The microphone is a bit bad.
Yeah, and the camera, I mean...
Yeah, well, we're in a test environment. Maybe they're not hearing it? Okay. I guess, guys, you're not now hearing it. I'm not super sure, but I'll just assume. So here is an example of what happens when you query Curious Bunch. You get these 4 digits here. Now this ping command is not really looking for the DNS. This is different type of command. Now if I want to just look at the DNS, I'll use the command dig, and I'll use curioussbun.ch, which will give me this kind of response. And if I want to query with additional like if you want to see the whole stack trace of like what is happening, what I can do is I can do plus trace curious bunch, and this is what's happening. So first we ask these guys. These are the root servers. So my first question is, who is dot? And dot is kind of on the other side of curiousbun.ch. Imagine I'm querying for curiousbun.ch dot. This is something like that, what I'm actually doing, but this is hidden from you. But this is the full qualitative domain name. But the dot is usually omitted because it's always there, so we just ignore it. So here's what happens. These are the so-called root servers. This is where my first request will go. I'll first ask the root servers for .ch, and then the root server will reply with, here's where you can find .ch things. And here is where you can find curiousbun.ch. Now there is some optimization I think that is going on here, because apparently .ch now knows immediately about curiousbun. But in general, what you will see is first .ch and then you'll see curiousbun.ch. And this is what the response that you will get. Now you can see there are several A records. The A records represent the exact IP address. So this part here is called the IP address, these 4 numbers. Why there are 4 of them? For redundancy.
Wait.
So basically any of these IP addresses that you query, you get the same address.
Oh, so the IP address is not unique. I mean,
yeah, you can have multiple.
A couple.
Yeah, you can have multiple of them. You don't have to have one. You can have multiple IP addresses mapping to one domain, or multiple domains mapping to one IP address. You don't necessarily have one-to-one mapping.
But they don't change.
They can change.
Over time.
Yes, they can change. Here is, by the way, a reason of why in the first 48 hours we didn't actually, our viewers weren't able to access our website through curiousbun.ch. Because the propagation of .ch, and I'll talk about this when we talk about caches, the .ch propagates the domain name in about, I think, if I can see it from here, I'm not sure.
6 milliseconds?
No. These are milliseconds, right? But this is a different kind of
thing.
Yeah, this is a different record. This is not an A record. We're looking for NS records, which this is time to live. By the way, these are in seconds, the time to live. So this is about, what is that? 700 seconds. So this is about more than 15 minutes, right? Something like that. Anyway, the time to live basically tells you how much time a caching server can cache the address for. And what the .ch had at the time was about 3 days. So the .ch would not know anything about curiousbun.ch for about 3 days or within 3 days, and you have no guarantee when it will happen. It will propagate in the next 3 days, but you don't know when, and there is nothing you can do about it. So basically you can wait for 1 day or 2 hours or 2 days, and nobody, no matter how you register your domain, there is no guarantee upon what's going to happen.
Wow.
Yeah.
Okay, and for how long was the error for?
So I think we got it resolved. So you can actually trace that if you go to trace, let me see, DNS propagation, and then you can see global DNS propagation checker is just a site where you can check, for example, for curious, I'll just zoom it a little bit, for curiousbun.ch, how fast has it propagated. So now here maybe these guys got their servers correct or something, but if I change my URL now, if I change my A record now to curiousbun, so you have a bunch of servers which are querying this curiousbun, and then it's trying to see if they're resolving to the same thing, and then you get checkpoints if they have resolved it or X's if they haven't resolved it. Why these guys haven't updated their servers, who knows? There is nothing we can do about it at this time for the DNS propagation. Let's try, just for the sake of it, let's try google.com. Well, as you can see, even here it fails, so maybe these servers are badly configured. If Google hasn't been able to propagate, probably no one has been able to propagate. Or we have large-scale BGP issues, which is a different... BGP is Border Gate Protocol, it's another TLA. but it's in a high level. There are many things that happen, right? And we still haven't even resolved that. Well, we kind of resolved our address here. So let's say we resolve it, right? Let's switch back to camera so that you can see our pretty faces. Is this one? I think this one. Yeah, okay. Hello again. And now we saw some backstage of like what we're doing actually on this computer, because we just have like 2 computers. All right. So you said there were some questions, and the questions were about the microphone. I'll try to lower my levels, but I'm...
Yeah, and for some news, but I'll just skip those questions.
Yeah, skip
I'm
these.
sorry.
Yeah.
I mean, just protect them, please.
Right. Maybe the microphone levels are better now. I try to just lower the sensitivity of the microphone. Let me know, guys.
Sorry, guys, we're just improvising.
Yeah, we're just improvising as much as we can.
Oh, well. So, we got back the IP address?
Okay, so yes, we got the IP address, which is the equivalent of the latitude and longitude in a normal, let's say, in a map. Yes, in a geographical area.
Okay.
Right.
Cool.
So what do we do now with this IP address, right?
Yeah, because I still need some information on the page.
So as we saw, as we said, there are many layers upon which the internet is working. So your computer needs to connect in some way to the internet, right? And there are multiple ways. So did you stop or something?
No, I'm just...
Oh, you just want to see yourself, okay.
It's alright.
It's alright.
So,
your telephone, or oh my god, who says telephone? Never mind. I'm just old.
You're just old.
Yeah. Okay. So your iPhone? No, it's not everything's iPhone. Anyway, so your phone can connect in 2 ways, right? You can turn on your Wi-Fi, or you can turn on your 4G or 3G or whatever network. But it basically uses some kind of radio signals in order to connect to the next hop.
Mm-hmm.
With your laptop or with your desktop computer, you can also plug a cable. So what we call this is, we call this layer 1, and this is called physical layer.
Okay.
Right? Because it's literally physics. So you can modulate the signal on the LAN cable, on the copper wire that connects to the router or to the next hop or to the wall on your socket or whatever, or you can use a modem. I never used a modem, by the way. I'm not that old, or I just didn't have a modem, or I didn't have money for a modem, but I never used modem. But it basically, you still connect with a cable through the telephone, through the modem, through the telephone, and then off to the wires. But basically, that's still, yeah, but that's still physical layer. So all these cables, or the connection with the Wi-Fi or with the 4G, this is still a physical layer.
Okay.
So what you do, and maybe you can explain a little bit better here, is you change the voltage on that cable. And when you increase the voltage above a certain, let's say, threshold, let's say 5 volts, when you increase the voltage, this is registered as 1. When you don't have a voltage on that cable, you have a 0. And you keep that voltage as a square wave or square wave estimation for certain milliseconds or microseconds or picoseconds. I don't know how long they are, right? But let's say, 5 microseconds of 5 voltage is a 1, right? And now here comes an interesting question. What if you hold this for, let's say, it's 5 or 1 microsecond, right? If you hold it for 3 microseconds, is these 3 ones? Sounds like it. But the more you increase the number of ones which are consecutive next to each other, the more likely you may have an error. So it's very easy to recognize if it's just a single one, and you held the signal for just 1 microsecond. But if you have a 10 ones,
probably it's an error.
You may have 9 ones, or you may have 11 ones, or you may have 10 ones, right? Okay. Because the error becomes like because you increase the space through which you have to hold the signal, right? So it's very hard to recognize, whether it's 1 more 1 or 1 less 1. Which is important because then you introduce errors. Or you can have spikes. So you can have just a random noise. You can have a random noise in the Wi-Fi modulation, or some kind of interference happening, some small or heat. I don't know, atoms just bouncing on the cable or something, and then creating just random noise on the cable, which just happened to pass that threshold for a while, which would register as a 1. So what you need is so-called error correction. And that's when you go into layer 2. And layer 2 depends again on the medium. By the way, so the internet is layered, right? So you have layer 1, which is the physical layer, and you have layer 2, which is trying to correct these errors, right? So let's say you have like 10 consecutive ones. Well, there are algorithms, and I'm not going to go into them, but we can share and we can just make a whole new post about it. You stuff like in between all these ones. I think we may be skipping a little bit, but that's the best internet connection we have right now, so we gotta deal with it. We may have to stuff a few zeros in between these ones and then correct them on the next layer, and we can create checksums for this. I don't know if that makes sense.
Kind of.
Yeah, but imagine you have a simple checksum where you check how many, like you send a packet of maximum 20 digits, and then the 21st digit is a checksum, or how much information have I sent with the previous segment, right? So if there is some kind of discrepancy between the data that I sent and the checksum that I sent, then this segment is discarded and we say retransmit again.
Okay.
So that's a retransmission on the physical layer. And that's what the second layer cares for. It tries to...
What was the name of the second layer?
Oh my god. Linked...
Wait, it was
physical layer... Oh, I'm sorry. No, it's... second layer. I think it can sometimes be called Ethernet. So Ethernet works on layer 2. Data link layer, I'm sorry. Just blank. Data link layer. So the second layer is called data link layer. And what you have is these kind of different error connections, or you can have retransmissions. So if you have, let's say, our two laptops are currently connected to one router and one access point, and they're basically both trying to send signals at the same time. If they both use the medium at the same time, well, then there's going to be a collision, right? A collision is basically when things overlap. So you don't know where the zeros and the ones end for one packet and when the zeros and the ones end in the other packet.
So we need to transmit them in slightly different times.
Right. So what you do is there are many different ways in which you can resolve that thing, and that's why I say it's so interesting, because you have both physics and computing science, and it's not necessarily only about networking. You have computer science on a layer of how do you resolve something on the physical layer. Right, so you need to retransmit the two messages in slightly different windows, right? You transmit the one, I'm sorry, and then the second. But it's a complicated thing. How do you ensure, like, how much time do you wait? Well, one way is to try to sense the environment around you and try to...
Yeah, you're trying to be listening to...
Try to listen, yeah. So this is collision detection and with sensing, and it's called EGZA or something like this, but it's basically an algorithm which tries to detect right now in use, and if you see it's in use, then you don't send your message. And if you see it's free, you try to send your message. But what happens if both try to sense that the medium is now free and then both transmit? Well, then you introduce a little bit of delay, of random seed of delay between these two segments that you try to send. So you say this laptop just generates a random number of microseconds or whatever that it needs to send this packet, and this computer generates another number, and then they try again. And if they fail again, they generate a larger number. They multiply it a little bit more so that there is less chance that things will start colliding.
Oh, that's smart.
Right, but that's why if you have a lot of devices connected to the same router, even though you have enough bandwidth on the router, you can still decrease the performance of everyone's network, because you increase the probability of things starting to collide. Right? Imagine you have 10 megabytes bandwidth on the router, but you have 10 devices. Well, what your limit is going to be is actually these devices fighting on the physical layer, trying to all access the same point.
Not the router.
Not the router itself.
My provider being like...
Right? But then you don't know. As a user, you have no idea, and you just say, well, my internet's slow. Right? Because you don't know which layer the problem is at. And it's kind of hard to actually recognize that. It's not so simple. You need kind of complicated tools.
Yeah, what about the router telling me if I can use it for 10 or 15 minutes?
I'm not sure. There might be devices like that, but basically that's also a limiting factor, like how much data you can send with how many devices.
That's why in a hotel with so many people.
Yeah, we can have some problems. Yeah.
Yeah, for example, lagging.
I think
so
we may be
annoying.
having some lag.
Can you try to? Yeah.
Are people saying that it's lagging a lot?
I cannot really see the comments.
Okay.
So maybe I just
Yeah, sure. We'll just get a break, get a Kit Kat or something.
No.
No, we're good.
Are we? Okay. Kind of. We're lagging a lot.
Yeah.
Yeah. Oh well.
Do you want to cut it short? I mean, if we're too
I can try
annoying.
to maybe if I close my computer.
It might help, yeah.
Yeah,
if you
I
want
mean, from what I learned.
From what you learned, yeah. I mean, but basically, I mean, right now in the hotel, I think there is some kind of conference happening downstairs, and they're having like a lot of usage, so it might not be the best. But we're hoping for the best, and we just keep on streaming, and anybody who wants to listen. All right.
Okay,
So,
I'm curious. So
yeah. So just let's keep talking.
Yeah, of course.
Okay.
So
right. So we're layer two.
Okay, just to revise.
Mm-hmm.
So we got the physical layer,
Mm-hmm.
which was how we are actually transferring the data over the air or the cable or something. And then because this has a lot of errors, so we need to be sure that we are transmitting the proper amount of zeros and ones, and the signal is
non-corrupted.
Yeah. So we have the data linked layer, which is accounting for those layers.
Yes, for those errors, yeah, on the previous one.
Right, and we talked about how we are listening, how our device is listening to send the package in proper time, and all that. And okay, let's say we have sent the package.
We're not there yet. Yeah,
no,
we're not there yet.
Okay.
We kind of resolved our. And by the way, just so that we make it clear, the DNS resolution happens on these layers as well. We're not skipping layers, right? But we're just trying to explain on the top down and on the bottom up as well at the same time in a way, because it's really complicated things that happens on all these layers, right? When you try to do the DNS resolution, it also uses the physical layer, obviously, and also uses the data link layer in order to correct these errors. And now the differentiation will start appearing in the higher layers. So, by the way, there are 7 layers, just so you know what is the scope of the whole thing, right? So, but we're going to basically talk about 2 or 3 more layers. So we're going to mix a few of the top layers in one, because it depends how you count. Right.
So they're not like super separated in a way.
Actually, they kind of are, but yeah, I mean the top layers are a little bit more mixed than the bottom ones. Let's say the bottom ones, the physical layer, the data link layer, they're really kind of well defined. Their boundaries and what they do most of the time. The IP layer, which is the network layer, which we're going to talk about now, is on top of it and is one of the few that are using very, very few protocols there. It's pretty much IP is the kind of the bottleneck of protocols. Like if you imagine it as kind of an hourglass way, the physical and the data link are on the bottom part of the hourglass, and then the IP is on the middle, and then you have another explosion of protocols which happen on the higher layers as well. So let's say we corrected all of these codes and we sent some kind of correct zeros and ones. That's what happens after the second layer.
Okay.
What we have ensured is that we were able to send the proper zeros and ones to the router to the next hop. But by the way, that also happens on the hop, not only from your computer to the router, but also from the router to the next one, and from the next one to the next one, etc., 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 up until the server. So what you have is a client, which is your browser, and the server, which is, let's say, curiousbun.ch or google.com or whatever it is. But in between these layers, all these physical layers, they still work, but they're in different mediums. So you can have optical cables connecting the different routers, which is very high distance, and they pretty much move with very, very close to the speed of light, if not the speed of light, or the speed of light in the medium of the optical cables, basically.
Yeah.
In glass. Yeah.
So.
Right. So, let's say we send these packets at least from this point to the next point, to the router. Right. Well, how do I know the address of the router? That's also kind of responsibility of layer 2. You also need to know what is the address of the router, but this is not necessarily an IP address. It's called a MAC address, MAC. It's Media Access Control. That's another theory. So when you see a MAC address, you see another bunch of digits. Right? So these are not the IP addresses, which we've talked about before, but these are MAC addresses. So this is addressing on the second layer. So for example, when you connect the cable from your computer to the router, which is just another instance of a computer, they know each other and they communicate to each other on these addresses. They communicate with each other on these MAC addresses.
Those are like the names of the devices, in a way.
Yes, on the hardware devices themselves. Think of it this way. The MAC addresses usually, like, they are 6 hexadecimal numbers. Hexadecimal number is just like any number, but just in the hexadecimal, right? Hexadecimal, it's like a number in base 16. So you can use all the digits from 0 to 9. So in
and then you have the letters.
Right.
Okay,
and then you have the letters from A to F.
Okay.
Right. So what you have, how you count in a hexadecimal, just really quickly, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then instead of 10 you have A,
B, C,
D, E, F, and then instead of 16 you have 10. And that's how you count. And then it's 11, 12, 13, 14, 15, 16, 17, 18, 19, 1A. Right?
Okay.
Right? Does that make sense?
Yeah.
Yeah, kind of.
Right.
You instead of having 10 possibilities, you have 16 possibilities. Like, let's just pick another system, let's say base 5. You have the digits from 0 till 4. So in base 5, the counting will be 0, 1, 2, 3, 4, 10, 11, 12, 13, 14, 20, 21, 22, 23, 24, 30, etc. Because the only things which you can use is the number from 0 to 5. In binary, you can only use 0 and 1. Mm-hmm. So it's 0, then you overflow 1, then you overflow, then it's 10, then it's 11, then it's 100, then it's 101, 110, 111, 1000. That's how you count in binary. Okay, so MAC addresses are in hexadecimal. So there are 6 hexadecimal digits, like A6, B5, AA, etc. And they're separated by colon, usually. In Windows, they're separated by dashes. It's just a convention, just to be harder for people. So that you copy something and you copy it and it's a mess and you're like, why?
It's not biased at all.
Okay.
So,
these devices on the second layer, they communicate with these addresses. But this is the abstraction for the hardware communication layer, right? The data link layer still works on the kind of helps the physical layer in order to correct its errors and to connect to each other. Mm-hmm. But the addresses, which we're going to talk about now, they're more logical addresses. Their IP addresses are the logical device. So if I change my router, its MAC address will change, but its IP address will stay the same. Right? So
say that again.
Okay.
I got distracted.
So imagine a router, right, has 2 addresses. One is a MAC address and one is an IP address.
Okay.
Well, it actually has more addresses. We'll just keep it simple. Right, so MAC address is the address through which your computer on layer 2 will connect to the router. Mm-hmm. So your computer has a MAC address and the other computer, which is the router, has another MAC address. And then they will communicate these error corrections and all this sensing of the medium, etc. will happen on this layer, on the MAC address. But then you have another abstraction, which is the third layer, which is the networking layer, where you have these numbers, which we just saw, the ones that were on the terminal, which are the IP addresses. And so you can change the router, and the MAC address will change because the MAC address is bound to the router hardware device itself, but the IP address will not change because the IP address is an abstraction above the physical layer.
So the IP address depends on where the router is situated, like physically situated?
More like in a way, but it's mostly given by something like some authority. Like this address is given by some authority.
So the IP address is not changing.
Let's say it's not. It can, but
okay.
Let's say for the understanding of what the difference between a MAC address and an IP address is, the IP address doesn't change.
So why do we need MAC address at all?
In order to be able to communicate between 2 devices and to recognize which these 2 devices are in hardware terms before connecting to IP addresses, which are more semantic way of representing because an IP address doesn't necessarily stand for a device. An IP address is an abstraction. It can hide multiple devices behind it.
Okay.
One of the reasons.
Fair enough. And also IP addresses are more limited in number?
That's another problem. That's another problem, yeah.
Okay, so we have the
By the way, a
address.
few of the things they're like, I'm not sure about exactly the history of the internet, right? But think about it this way: the internet was never intended to be that big, like initially, right? We have done patches upon patches of things happening there. Can an internet be invented in which a MAC address and the IP address are the same? Absolutely, yeah. Why not? I mean, if you use IPv6, which is an extension of the IP address which we use now, you have enough addresses in IP in order to account for all the devices in the world and all the possible atoms in a gazillion universes that you can have, right? So even if every atom is a device, you can still account for them. There's so many addresses there, right?
Okay.
So that's the extension of the IPv4. The IPv4 can contain just 4 billion addresses, roughly.
Just.
Right. But 4 billion back in the time when there were about 4 billion people on the planet seemed like infinity.
Yeah.
And when there were like thousands of computers, right? And just tens of them were connected to the internet.
And now it's not.
And now it's just everybody has like at least 2 or 3 devices. Well, at least in like 3 billion people have more than 2 devices, per person. So we run out of IPv4 addresses. This is the third layer, the networking layer addresses, and they extended to IPv6. Why we skipped 5? Who knows? We skipped 5. We just don't know. There is maybe a trivia history page on Wikipedia that can tell you about it. But we skipped 5. We just jumped from IPv4 to IPv6. What happens to 1 to 3? Who knows? There is a history page somewhere. I don't know. Right. But basically, yes. Can you just like decide? It's a good question, right? I don't know exactly the answer, but my best guess is historically, MAC addresses were developed after the IP addresses, and we needed to account for more devices. And by the way, you can change your MAC address. Like you can run a command on your computer to change to masquerade your MAC address, and there's some interesting security attacks which can happen on that. Like you can change your computer's MAC address, or you can change your router's MAC address, etc.
I'm sorry. I'm sneezing.
Oh yeah. By the way, he has some allergies, so sorry about that. We still don't know whether we are transmitting. We hope
Can
we
you
are.
check the comments?
Right. I think my computer might be a little bit slow. We have IPv6
Yeah.
and IPv4. They do not want to reinvent it. It could be done a lot better, but instead they just introduce fixes on top of bugs. Yes.
Yeah. If it's lagging, it's annoying.
All right, and they say we should be speaking a little bit more to the camera rather than to each other. And yep.
Oh,
okay. Well, it's.
Okay.
Thank you for the feedback. That's right.
Fair
Right.
enough.
So
But if it's lagging, that's annoying.
it is annoying. I'm sorry. I hope that the voice is not lagging too much. So I hope at least you hear the
Your
speaking.
beautiful voice.
Yeah, I don't know why the computer, but I think it might be the computer as well that is lagging. It might not be only the network layer, so I'm not sure. I'll stop sharing the screen. That will happen a bit. Okay.
Do you want to try to cut it short?
Yes, I'll
And
try
maybe
to
continue?
cut it short. Maybe we'll continue next time. We tried to prepare a little bit for this one, but we've been on vacation pretty much the past week, but we just didn't want to skip. Yes, and also Vasil is in a conference, right? So he was not able to join this week, and we decided to do this kind of improv conversation, let's say, right now.
I think it's going well. I mean, I learned some stuff,
Yeah.
and I was curious about it. So,
Yeah, we were curious.
and let's try to finish this conversation next
Right.
week,
Mm-hmm.
and we'll have it like I'll probably have like a quick summary and everything.
We can, yeah. I'm thinking. I mean, this, depending on how interested people are, this is a huge topic and can span into like multiple. Or we can basically explain that you have like the simplest version, just for TLDL, too long didn't watch or didn't listen. Basically, what happens? You have a client, you have a server, you have to connect them somehow, and every time you type a URL query, you have to talk to each other, and there's a lot of layers in between because you have to respond in under a millisecond or under a second. So there's a lot of redundancy layers upon redundancy layers which are trying to fix things, and the internet has been an ongoing development thing that hasn't been invented. Like it's been more an evolution rather than an engineering intelligent design. So we've been trying to intelligently fix problems which we've introduced previously, to account for errors, and we're also trying to cover the errors which are happening just because the world usually introduces errors based on physical problems, of routers being changed, of things being moved, of things being far away, of things being updated. And so it blows my mind that it even works.
In seconds.
Yes,
Milliseconds.
most of the time.
If you have internet.
It's crazy.
Thank you guys for tuning today, and we are really, really sorry for the circumstances and for lagging, and maybe just don't watch us, just listen to us, hopefully. And we will definitely continue with this conversation next week, and yeah, at some point, because I still want to learn how did they do this page?
Yeah,
What's going on?
It's crazy, and maybe I'll be back at home, and I'll have a little bit more setup and a little bit more stable internet, whatever that means.
And a better camera.
Yes, yes. And subscribe, ask questions if you still guys interested, or if
give us feedback.
If that's completely boring to you, just say it, we'll skip it. So talk to other people as well who are maybe interested in these kind of topics, and let us know.
Thank you guys. See you.
Bye bye.
Bye.